Assuming you went through that dark opening, you would arrive at one more universe. There is presently an association between quantum processing and dark openings. In this educational video, we investigate a noteworthy and frightening disclosure made by the James Webb Space Telescope inside a dark opening, explained by none other than Bill Nye the Science Guy. A dark opening is a star so huge that, indeed, even light can't escape from it due to its tremendous gravity. The secrets of dark openings have baffled researchers for many years. However, presently, on account of remarkable capacities, we've witnessed something really shocking. The very huge dark opening consumes what could be compared to one Earth every day. The staggering and convincing. The very first picture of a dark opening in space. Prepare yourself as we dig into the unimaginable subtleties of this infinite disclosure and what it could mean for how we might interpret the universe. Stars toward the finish of their life, much greater and more gigantic than the sun, run out of fuel and begin to break down as gravity squashes them. Dark openings are interesting to recognize. It was, in fact, a test to look for the initial one. Despite the fact that Einstein's theory of relativity predicted they were common, dissimilar to stars, dark openings don't emit any light through their own effort. Their size and spin are the only measurable properties. We have visual proof of dark openings affirming their reality, which has recently opened up. Anyway, definitive confirmation of dark openings was lacking for a long while. The first dark opening, Cygnus X-1, was found in 1964, yet it took more than 30 years for specialists like Stephen Hawking and Kip Thorne to reach an agreement on whether Cygnus X-1 was indeed a dark opening. Hawking, a noticeable figure in dark opening research, was sure about their presence but wary about the absence of conclusive discoveries. Hawking and Thorne were nearly 100% sure that Cygnus X-1 was a dark opening in 1975 when the bet was first cast, and by 1988 they were 95% sure. Still, they held on until 1990 to yield to proof when more observations provided adequate confirmation. The initial disclosure of Cygnus X-1 was made utilizing 2 Geiger counters sent off into space on a suborbital rocket, detecting a signal pinpointed to a system 7,200 light-years away. The system featured a blue supergiant star orbiting another enormous object, transmitting strong X-rays, which would make sense if it were a dark opening. Much research has focused on Cygnus X-1 since its disclosure, revealing that it is 21 times the mass of the Sun, making it the largest stellar mass dark opening found. Without gravitational waves, this revelation challenges long-held suppositions about dark opening formation and the mass loss experienced by stars over their lifetimes. Cygnus X-1 breaks records in more ways than one. Its remarkable mass and the fastest rotational speed of any dark opening found up until now, approaching the speed of light, defy the accepted pattern of dark opening development. Although authoritative proof of dark openings has only recently been found, it is increasingly evident that they are dispersed throughout the universe. Even assuming researchers eventually unravel all the secrets of Cygnus X-1, the first of its kind, countless others still hold many surprises. Under 2,000 light-years from Earth, researchers have found a dormant beast, the Milky Way's largest stellar mass dark opening, Gaia BH3, with a mass multiple times greater than that of our Sun. Despite being the second closest known dark opening to Earth, Gaia BH3 remained unseen until now. Gaia BH3 was found accidentally while researchers from the European Space Agency examined data from the Gaia mission, which maps our galaxy in 3D. The discovery of this dormant dark opening, which isn't actively siphoning energy and material from a companion star, was a complete surprise. Normally, stellar mass dark openings in our Milky Way have a mass multiple times that of the Sun, with Cygnus X-1 holding the record at 21 times the Sun's mass. However, Gaia BH3, with a mass of 33 solar masses, is still small compared to all dark openings. For example, the central supermassive dark opening in our galaxy, Sagittarius A*, is 4 million times bigger than the Sun. Gaia BH3 is the second closest dark opening to Earth, behind only Gaia BH1, which is 1,500 light-years away and multiple times the mass of the Sun. Cosmologists currently have more proof to figure out how stellar mass dark openings form. Dark openings from the end of massive stars with lower concentrations of heavy metals are believed to be the source of more massive stellar mass dark openings. These metal-poor stars, mainly made of hydrogen and helium, are thought to experience slower mass loss, leaving more material available to form massive dark openings when they die. Utilizing the James Webb Space Telescope, JWST, experts have found an incredibly red, very massive dark opening existing in the early universe's shadow. As the universe expanded, the supermassive dark opening took on a reddish color 700 million years after the Big Bang. The light traveling our way is redshifted, suggesting a thick layer of gas and dust surrounding the dark opening. Lucas P. Finkel and Avi Loeb of the Ben-Gurion University of the Nejef's Cosmology Group calculated the dark opening's mass using JWST data, finding it to be around 40 million times the Sun's mass. This revelation stands out from the universe it inhabits, showing that the very massive dark opening is rapidly consuming the surrounding dust and gas, situated around 12.9 billion light-years from Earth. This quasar was initially recognized by its red appearance. Quasars are made when a lot of material surrounds supermassive dark openings, forming a disk of gas and dust that feeds the dark opening. The immense gravitational influence of the dark opening disturbs this matter, producing extreme temperatures and making it shine. The light emitted by quasars can be so bright that it outshines all the stars in their surrounding galaxy. The JWST identified this very massive dark opening as a small point due to the enormous amount of radiation it was producing. The object was initially identified as an unusual star-forming galaxy, based on color analysis supporting the hypothesis of very massive dark openings. Its small size and extremely massive nature stood out from other quasars found in the early universe. This discovery was made possible by gravitational lensing, an effect predicted by Einstein in 1915. Einstein's theory of general relativity proposes that objects of mass warp the fabric of spacetime, which combines as a single entity called spacetime. This curvature causes gravity to exist, and the more massive the object, the more extreme the curvature. The curvature of spacetime also affects the light emitted by stars, bending it as it passes near massive objects. This phenomenon, known as gravitational lensing, allows us to see distant objects that are otherwise invisible. The JWST utilized this effect, aided by a galaxy cluster called SMACS J0723.3-7327, to amplify the brightness of distant galaxies and reveal the red quasar. This new data adds to the growing body of evidence that the early universe was populated with very massive dark openings, which can be millions or even billions of times heavier than the Sun. Now that this phenomenon has been observed in numerous early universe supermassive dark openings, it sheds light on the development of both the dark opening and the host universe, as well as the connection between the two. The classic chicken or egg problem, though on a galactic scale, remains unresolved. Did the galaxy or the dark opening come first? How large were the first dark openings? And how did they evolve? Researchers may have found evidence that microquasars, which are dark openings consuming power stars, are cosmic particle accelerators releasing unexplained high-energy astronomical beams that hit Earth. These massive dark openings consume material from nearby supermassive stars in binary systems, and some of the stellar matter is expelled as relativistic jets traveling at incredible speeds. Microquasars are smaller versions of quasars, both fueled by supermassive dark openings consuming nearby matter. In 1912, high-energy particles could hit Earth with energies reaching 10 to the power of 20 electron volts, significantly more energetic than particles accelerated at the Large Hadron Collider, the world's most powerful particle accelerator. The theory suggests that supermassive dark openings and microquasars are the universe's most intense particle accelerators. However, evidence of microquasars accelerating particles to such high energies has been scant until now. Using the High-Energy Stereoscopic System, HESS, researchers identified extraordinarily high-energy gamma rays from the jets of the most powerful microquasar in the Milky Way, establishing a connection between cosmic rays and microquasars. The microquasar SS433 produces high-energy gamma rays through its jets, which interact with surrounding matter, creating a shock front that accelerates electrons to extreme rates. These gamma rays are a result of this interaction. SS433 was the first microquasar ever discovered, situated at the center of the W50 supernova remnant, affectionately called the Manatee Cloud. SS433 has been the subject of extensive study for many years. The system consists of a white supergiant star and a dark opening about 10 to 20 times the Sun's mass. They orbit each other every 13 Earth days, with the star's outer layers being stripped by the dark opening's gravity. Some of this material forms an accretion disk around the dark opening, while other parts are ejected as jets traveling at 26% of the speed of light. These jets spiral in a wobbly pattern, shaping the W50 supernova remnant and giving it the appearance of a cosmic manatee. The jets fade over time but reappear as a phenomenon driven by the recurring nature of SS-433's activity. The jets from the dark opening also interact with the surrounding matter, creating a complex interaction between the dark opening and its environment. This behavior makes SS-433 one of the most fascinating and enlightening objects in the study of microquasars and their role in cosmic particle acceleration. Despite SS-433 being the first identified microquasar, much remains unclear about how dark openings accelerate particles to such extreme energies and their broader impact on the universe. Researchers use various methods, including indirect measurements, to understand these cosmic phenomena. For example, dark openings can be observed through their interactions with neighboring stars and matter, as evidenced by the dramatic increase in X-ray emissions as material is pulled into their gravitational grasp. This phenomenon is crucial in understanding dark openings and their influence on the universe, providing essential insights into the evolution and behavior of these enigmatic objects. In the realm of dark opening research, the recent discovery of the most distant known dark opening, an unprecedented 13.1 billion light-years away, has further expanded our understanding of these cosmic giants. This discovery, made possible by the capabilities of the James Webb Space Telescope, JWST, reveals a very massive dark opening formed less than 1 billion years after the Big Bang. This early formation challenges existing theories about dark opening development and galaxy formation. Observations suggest that these early dark openings may have played a significant role in shaping the structure of the universe by influencing the formation and development of the earliest galaxies. In addition to their role in galaxy formation, dark openings have been linked to powerful cosmic phenomena known as active galactic nuclei, AGN. AGNs are characterized by extremely luminous emissions from the regions around supermassive dark openings at the centers of galaxies. This emission occurs when material from the surrounding accretion disk is heated to extreme temperatures as it spirals inward, emitting X-rays and other forms of radiation. Studying AGNs provides valuable insights into the feeding behavior of dark openings and their impact on their host galaxies. These studies have shown that AGNs can significantly influence galaxy evolution by regulating star formation and dispersing heavy elements throughout the galaxy. Recent advancements in gravitational wave astronomy have provided a new way to probe the properties of dark openings. The detection of gravitational waves from merging dark openings by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo has opened a new frontier in understanding these elusive objects. Gravitational waves, ripples in spacetime caused by accelerating massive objects, allow researchers to measure the mass, spin, and other properties of dark openings that are otherwise difficult to observe. These observations have confirmed the existence of dark openings with masses ranging from a few to several solar masses, including the detection of dark opening mergers resulting in the formation of even more massive dark openings. Another intriguing aspect of dark opening research involves their role in the production of high-energy cosmic rays. Cosmic rays, highly energetic particles traveling through space, are thought to be accelerated by dark openings, particularly those in active galactic nuclei or microquasars. The process involves the interaction of relativistic jets produced by dark openings with surrounding matter, creating shock waves that accelerate particles to near-light speeds. Understanding the origins of these cosmic rays is crucial for deciphering their impact on the interstellar medium and the broader cosmic environment. In addition to their influence on cosmic rays, dark openings are also associated with the formation of complex structures known as relativistic outflows. These outflows are powerful jets of matter ejected from the regions around dark openings, traveling at nearly the speed of light. The study of these outflows helps researchers understand the mechanisms behind the formation and evolution of supermassive dark openings and their impact on their host galaxies. Observations of these jets, have provided crucial information about the magnetic fields and particle acceleration processes occurring in the vicinity of dark openings. Theoretical work has also explored the nature of primordial dark openings, which are believed to have formed in the early universe shortly after the Big Bang. Unlike stellar mass or supermassive dark openings, primordial dark openings would have formed from density fluctuations in the early universe rather than from collapsing stars. If they exist, primordial dark openings could account for some of the dark matter in the universe. Identifying these elusive objects remains a significant challenge, but their study could offer new insights into the fundamental properties of dark matter and the early universe. Furthermore, dark opening thermodynamics and the study of Hawking radiation continue to be areas of active research. Proposed by Stephen Hawking, this theoretical radiation suggests that dark openings could emit particles and slowly lose mass over time. While direct detection of Hawking radiation is currently beyond our technological capabilities, it has significant implications for our understanding of dark opening evaporation and the ultimate fate of these objects. Theoretical models and simulations are helping to explore how this process could influence the lifespan and properties of dark openings. Another fascinating development in dark opening research is the investigation of dark opening information paradox, a long-standing puzzle in theoretical physics. This paradox concerns whether information that falls into a dark opening is lost forever or if it can be recovered in some form. Recent advances in quantum information theory and holography have led to new insights into this issue, suggesting that information may be preserved in a highly scrambled form and potentially recoverable in some way. Finally, the detection of gravitational waves from dark opening mergers has not only confirmed the existence of these cosmic giants, but also provided a unique way to study their formation and evolution. These waves carry information about the masses, spins, and dynamics of the involved dark openings, offering a new method for probing the fundamental properties of these mysterious objects. Ongoing observation and analysis of gravitational waves will undoubtedly reveal much more about the nature of dark openings and their role in the universe. In summary, dark opening research continues to evolve with advancements in observational techniques, theoretical models, and new discoveries. From the distant supermassive dark openings in the early universe to the complex interactions of microquasars, the study of dark openings remains a dynamic and captivating field with profound implications for our understanding of the cosmos.